Everyone, and welcome to Spectral Geometry in the Clouds. Today it is our pleasure to listen to Keeler from Dalhousie University, who's going to talk to us about off-diagonal spectral cluster asymptotics on Zoll manifolds. As usual, don't hesitate to ask questions by unmuting yourself, or if you do so in the chat, we will convey them to the speaker. Blake, the floor is yours.
All right, well, thank you very much to the organizers for the invitation. It's my pleasure to speak to you today. The talk I'll be giving today is based on some joint work with Yaiza Canzani at UNC Chapel Hill and Jeffrey Galkowski at University College London. So with that, I will go ahead and introduce a bit of notation. So we're going to introduce a smooth, compact manifold without boundary equipped with a Riemannian metric G. And as usual, we'll denote the dimension by little n, and the dimension will be assumed to be at least 2. And we will introduce the Laplace-Beltrami operator denoted by delta sub G, and we'll take it with the sign convention that it is negative definite, just to be clear. So because the compactness of M, we have an orthonormal basis of eigenfunctions, which I'll denote by phi sub j, such that negative delta applied to phi j gives us back some eigenvalues lambda j squared times phi j again. They're normalized so that their L2 norm is 1. And these frequencies lambda j start at 0 and are listed in increasing order, repeated according to multiplicity. So some of them may be equal to each other. So I want to introduce now the spectral projection operator onto some interval in the spectrum. So I want to fix an interval I, which is a subset of R. And I will define the orthogonal projection operator pi sub I to be the orthogonal projection from L2 of M onto the direct sum of eigenspaces of the Laplacian, whose frequencies lambda j fit exactly in this fixed interval I. And in the eigenbasis on the previous slide, this quantity has Schwartz kernel pi I of xy, which is a function on M cross M, and it's given as this sum over lambda j in I of these pointwise products of eigenfunctions, phi j at x times the complex conjugate of phi j at y. And an interesting property of this Schwartz kernel is that if you take the trace of this operator, which is the integral of the restriction to the diagonal, we recover the eigenvalue counting function. It counts the number of frequencies in this interval I. Now, I'm going to be considering the case where I is actually dependent on some parameter lambda. So we'll consider a sequence of intervals, I sub lambdas, as lambda tends to infinity. A special case of this will be very familiar to many of you, which is just the interval 0 to lambda, which corresponds exactly to Weyl asymptotics. So the standard Weyl law and all of its great quantities of literature that have been written about it correspond to this choice of the interval I lambda. You're projecting onto all of the eigenvalues from 0 up to lambda squared. Now, I won't be talking about that case today, but it's worthwhile to note that that is it's an important setting to consider. I'll be focused on what I'm referring to as spectral clusters for today, by which I mean intervals I sub lambda, which have a length that are uniformly bounded above and below. So you can think more or less something like lambda minus epsilon to lambda plus epsilon for some fixed epsilon, or sometimes people consider the unit interval lambda to lambda plus 1. They're often more or less equivalent to each other. And the reason why you would consider such things, besides the fact that they have interesting properties in and of themselves, is that they appear frequently in the study of what are called monochromatic random waves. So in the study of a random wave that corresponds to these frequencies, say in this interval lambda minus epsilon to lambda plus epsilon, its covariance kernel coincides almost exactly with the Schwartz kernel of one of these spectral projection operators. So that's a reason why you might be interested in such objects, but they are interesting in and of themselves. And in general, in contrast to the Weyl law, where you're looking at the interval 0 to lambda, asymptotics as lambda goes to infinity are not known for such spectral clusters, pi I lambda, where you have a roughly fixed width interval. There are many cases where it is known, but there is no general theorem that states what the leading term in the asymptotic expansion should be as lambda tends to infinity. But there are some special cases where we can write it down, in particular on the round sphere, where obviously the geodesic flow is periodic, we can explicitly compute all of the eigenvalues of the Laplacian. I'll denote them by lambda L squared, and they are L times L plus the dimension minus 1. And they have very high multiplicities. There are huge gaps in the spectrum where there's nothing, and then you'll have an eigenvalue at one of these lambda L squareds, and their multiplicities are very, very high. So if you choose your interval to miss one of these eigenvalues, the projection is just 0, so that's not very interesting. But if we choose our intervals carefully, we can make sure that we capture these high multiplicity eigenvalues. And one way that we can do that, certainly not the only way, is to set this quantity nu L to be L plus n minus 1 over 2, and project onto the interval nu L minus a quarter and plus a quarter. And there's nothing very special about a quarter. It just turns out that that is good enough to make sure that we hit exactly these eigenvalues. Then it is known that for any x and y on the round sphere, whose distance is bounded above by some r sub L that tends to 0 as L tends to infinity. So as you move out farther and farther in the spectrum, we do want to be in a shrinking neighborhood of the diagonal. X and y should be getting closer and closer together. Then we can show that the projection onto one of these eigenvalues, which we've cooked up our intervals so that the interval exactly captures that eigenvalue, we get an asymptotic expansion that looks like this, where you have the leading power is like nu sub L to the power n minus 1 times this quantity that is based on the Bessel function of the first kind of order n minus 2 over 2, evaluated at nu sub L, the frequency, times the distance between x and y, defined with respect to the Riemannian metric, of course, and divided by a power of nu times the distance, so that this quotient is a well-defined smooth function all the way down to the diagonal. And the remainder in this asymptotic expansion is like little o of nu sub L to the n minus 1. So it is ever so slightly smaller than the size of the leading term. But again, in contrast to the general Weyl law, there's no like polynomial power improvement in the remainder. It is just the slightest bit better than the leading term. Another example where we can do things very explicitly is on the flat torus. So I'll denote that by t to the power n. And in this case, the geodesic flow is completely integrable, and it also stands in stark contrast to the sphere, because here the set of periodic geodesics has measure 0. It's countable, corresponds to, or at each point, I suppose it's countable because it corresponds to the rational angles. But here again, we could choose sort of any non-negative function r sub nu that tends to 0, and then for the distance between x and y shrinking, like r sub nu, the spectral projection onto, say, for example, nu minus a half to nu plus a half, we choose something different than a half, it's not that important. We get essentially the same leading order term, but for any sequence of nu. We don't have to choose them so that we capture these large eigenvalue clusters. We can just take any sequence of intervals that moves out towards infinity. And we get the same leading order term and the same remainder. Well, on torus, you could, I believe, do a little bit better, but because you have a polynomial improvement in the Weyl law. And the fact that these two give the exact same leading order term, despite the fact that their dynamics are so dramatically different, along with some other evidence that I will provide you in a bit, this leads us to a conjecture that regardless of the dynamics of your manifold, you should still be able to get this leading order behavior, even if, as long as you choose the intervals carefully enough. So if MG is a smooth compact Riemannian manifold of dimension at least 2 without boundary, and we fix some point x in M, then we conjecture that there exists a constant C positive and sequences nu sub L and epsilon L, where nu L tends to infinity, and epsilon L is going to determine the width of our intervals, and it's just going to be some bounded quantity. So that as long as the distance between x and y shrinks in the limit as we take L to infinity, then this spectral cluster kernel should look like this Bessel function thing, plus little o of nu to the n minus 1. And we also have this additional factor that corresponds to the spectral cluster evaluated at the diagonal. So this is where you get your nu sub L to the n minus 1 from on the previous slide. So this is the thing that's essentially accounting for the number of eigenvalues that live in this window from nu sub L minus epsilon to nu sub L plus epsilon. And this conjecture traces back to some work of Steve Zeldich for Riemannian random waves. And we've sort of updated the language a little bit, but it traces its origins back to some work of Zeldich, and it's related to, if you're familiar with it, Berry's conjecture in the field of monochromatic random waves. Now, in order for this to be meaningful, we do have to choose the intervals so that this on-diagonal quantity that sits in front actually looks like nu sub L to the n minus 1, because otherwise the remainder term is going to be too large and we're not really saying anything. So this is why, for example, on the sphere, we had to choose our intervals so that we actually capture those high multiplicity eigenvalues. So there's enough stuff in our interval to make a meaningful asymptotic. And also, as we've seen, this conjecture holds on the sphere and on the round, on the round sphere and the flat torus. Excuse me.
So
now, yes.
Can I? One thing that I somehow failed to. I mean, intuitively, I would have thought that you could say things not within any radius of the balls going to 0, but at, say, some length scale that corresponds to, say, 1 over root lambda or 1 over lambda, I guess, or 1 over nu in this case. Why do you expect this kind of thing to hold even for distances that are different from the characters?
So that's a good question. And I suppose I should leave a little bit of wiggle room in there, because it's in all of the cases where we have verified this, you can actually get a distance that just goes to 0, sort of like any rate. But I'm not aware of a conclusive proof why you should always get that. It's suppose an optimistic conjecture in that case. So perhaps you would need some kind of rate as you go to 0. But when you impose a rate, you are making a much weaker statement in some sense, because you could sort of get a lot of help from the Taylor expansion near the diagonal. If you have because factors of the distance will pop out, and then if you have some like polynomial improvement in the rate at which you go to 0, sort of cheating a little bit in that sense to get that extra remainder improvement. That's not to say it wouldn't be true. I believe that such things could be proven, but the hope is that you can get an arbitrary rate as the distance goes to 0. I don't expect that would hold if you wanted a better remainder. If you wanted some kind of quantitative improvement in the remainder estimate here, then you're going to have to impose some kind of rate at which the distance goes to 0. Because then the Taylor expansion of this thing you're claiming is the leading term actually starts to interfere, because you start Taylor expanding this near the diagonal, and you get factors of the distance that will hurt you if your distance is not shrinking faster than whatever your remainder improvement is. So for example, in the no conjugate points case, you can get a log improvement, and there you have to choose the distance tending to 0, like some square root of lambda over log lambda or something like that, or log lambda over lambda. There's some weird choice of rate that you can make that makes it all work. Sorry, there's a very long answer to your question. I'm sorry.
I mean, it makes things clear, I guess.
So a fairly general setting in which we can show that this conjecture always holds is in the non-self-focal case. So this was proved by Canzani and Hanin back in 2015, and with some improvements 2018. They showed that if you fix an x0 in M, which is non-self-focal in the sense that the set of geodesic loops emanating from x0 has measure 0 in the cosphere fiber at x0. So there are very few looping geodesics. Then for any rate that tends to 0, you have that the supremum over x and y in this ball of radius r nu centered at x0 of this quantity, where you take the difference between the spectral cluster. In their case, they use the interval nu to nu plus 1, but it's easily modified to other similar intervals, that you get the correct asymptotic behavior at a rate that is like little o of nu to the n minus 1 here. And furthermore, they actually prove something better, which is that you can take derivatives in x and y and maintain this asymptotic behavior. So you can introduce derivatives with multi-indices alpha and beta in X and Y respectively. And this corresponds to increasing the power of nu in your asymptotic expansion by the order of differentiation. Since in this case, the on-diagonal spectral cluster does indeed look like nu to the n minus 1 times this factor of the volume of the sphere divided by some 2 pi's. In this setting, we have conjecture 1 in any case where you have a non-self focal point. So on any manifold, if you can find a non-self focal point, then near that point, you will have this little o behavior for the spectral clusters of roughly unit width. And this is proved by first obtaining an improvement for the 2-point Weyl law, which is the projection onto 0 to lambda. So you get a little o improvement in the general Weyl law, which in turn gives you exactly this result. You just kind of subtract pi 0 to lambda plus 1 minus pi 0 to lambda, and you get exactly this result. And this relies heavily on the non-self-focal assumption to control the behavior of the wave kernel. And like I mentioned, this can be modified to other intervals of fixed size. So there's nothing special about nu to nu plus 1. You could look at nu minus a half, nu plus a half, or minus a quarter plus a quarter. Doesn't really matter. So this is a fairly general result. There's no global assumption here. You just need that the point that you're localizing near is non-self-focal. What I'm going to be talking about today is sort of the polar opposite setting, which is that of Zoll manifolds. So a Zoll manifold is one for which every unit speed geodesic is periodic, and all of the geodesics have a uniform period, capital T. So here's some nice pictures. The round sphere is sort of the canonical example of a Zoll manifold, but they don't all have to be the sphere. Here's another picture of a Zoll surface discovered by Zoll themselves in 1903, which is admittedly very much like a sphere, but it is a little bit flattened here at the top. And this red curve that is highlighted is one of those closed geodesics that has the uniform period, capital T. Now, a thing that's noteworthy, the reason this is sort of the opposite of the non-self-focal case, is that every point on a Zoll manifold is somehow maximally self-focal, in the sense that the set of looping geodesics at a point, it has full measure. It's everything, every direction. You travel in that direction and you are on a periodic geodesic of the same period. So you have this maximal self-focal property. And so the result on the previous slide does not hold anywhere on a Zoll manifold. Furthermore, it is fairly well known that the Zoll eigenvalues are strongly clustered near a fixed sequence, which I'll denote by nu sub L squared. This is analogous to the case of the sphere, where you have eigenvalues with very high multiplicity. You don't necessarily have the high multiplicities on a Zoll manifold, but you're kind of close to it. All of the eigenvalues are very close to this specific sequence, nu sub L. And this sequence, nu sub L, is defined as 2 pi over the uniform period times L plus this math frac A over 4, where this A is the common Maslov index of all of the closed geodesics. And because of this clustering property, Zoll manifolds actually saturate the remainder bound in the Weyl law. So there's no hope of obtaining a remainder improvement in the asymptotics for the full spectral projection from 0 to lambda. So the strategy that Canzani and Hanin used for obtaining the result of conjecture 1 is not available to us in this setting. In fact, Duistermaat and Gilliman in 1975 showed that the eigenvalue counting function corresponding to a fixed width interval around these nu sub L looks like some constants times nu sub L to the n minus 1. You get sort of the maximal growth of these eigenvalue clusters. And in fact, they proved something better than this. They proved that that most of the lambda j lie in a kind of shrinking window of size L to the minus a half, centered around the nu sub L. So for the context of conjecture 1, to choose my intervals so that there is enough stuff in that interval to project onto, these nu sub L provide the perfect candidates. So I'm going to choose intervals centered around nu sub L as my candidates for the centers of the spectral projection clusters. And with that, I'm ready to state the first main result, which is that on any Zoll manifold of dimension at least 2, uniform period capital T, I let nu sub L be as before on the previous slide. And for any epsilon positive, I'll define the following quantity. This RL or R epsilon of LXY defined as the difference between the spectral projection onto this interval minus the thing that I claim is the leading order term. In this case, we get a factor of 2 pi over t because that's the size or the number of eigenvalues in that, or it's a constant that appears in the expansion of the number of eigenvalues in that interval. Then we have the following property of this remainder function, R sub epsilon. We can, as long as we take epsilon small enough, and it doesn't have to be particularly small, it just has to be smaller than 2 pi over the period, we have that the supremum over all distances less than epsilon, we take the lim sup as L tends to infinity. We have to take the lim sup here because the limit may not exist as you go out in the spectrum. You'll have potentially some residual thing that depends on the distance between X and Y. And then as you send the distance between X and Y to 0, you get the correct asymptotic. So this remainder tends to 0, or rather it is little o of nu sub L to the n minus 1, and then you modify it with the number of derivatives that you've taken in X and Y.
I have a question. Is if Colin Verdier, I have a question. Is it important to center the interval on nu L, or you can take nu L plus epsilon, or is it important?
It is important to make sure that you are at least a little bit on either side of nu sub L, because there are potentially big jumps in the spectrum as you cross the nu sub L. So for example, on the sphere, if you made your interval, one of the endpoints of your interval exactly the eigenvalue, you would run into some regularity issues in running the techniques of the proof. Because I
understand, but there is in general a limit density which is smooth on some intervals, so you can take this kind of a subinterval of the.
It is possible that you may be able to get the endpoints to be nu L. I would have to double check some elements of the proof to be sure. There are some places where the regularity may be an issue because we have to estimate the kind of the size of the jumps as you move across these.
But you expect that generically you have a smooth density of the eigenvalue in some in the cluster interval, and then probably I don't know. But okay.
I would say in general probably, but there might be some exceptional examples like the round sphere.
Okay. I understand that.
Okay. Yes, so what we have is that on any smooth Zoll manifold, the spectral cluster centered on these nu sub L has exactly the desired asymptotic behavior, as long as we take limits in the right order. And I will sketch the proof in the case where we don't take any derivatives, because the modifications when we take derivatives are very, very small. It changes some powers of nu sub L that pop out, but largely the proof is identical. So I will assume that we do not take any derivatives. So the first thing I'm going to do is relate the spectral clusters to the half-wave kernel, which is a fairly standard technique in the study of spectral projection kernels, where we're going to take Fourier transform in lambda and end up with something that is related to the half-wave kernel on the Fourier side. So I'll introduce some notation here. I'll let this 1 sub minus epsilon epsilon to be the characteristic function of the interval minus epsilon to epsilon. And then I will simply rewrite for any lambda the spectral projection onto this interval, lambda minus epsilon to lambda plus epsilon, as a sum over all j, where I introduce this cutoff function of with epsilon evaluated at lambda minus lambda j. So I have done essentially nothing here other than add a bunch of zeros to my sum. And then I will introduce a Schwartz cutoff function to sort of smooth out the behavior of this spectral projection as a function of lambda. So on the lambda side, I'm going to convolve with this cutoff function rho, which will correspond on the Fourier side to restricting the support of my half-wave kernel. So I want the support of rho hat to be contained in some interval -2 to 2, and rho hat to be identically 1 in a neighborhood of 0. So say -1 to 1. Doesn't particularly matter as long as it's fixed. And then I will also introduce another parameter to give us a little bit of wiggle room to sort of scale the size of the support of rho hat. For any sigma positive, I'll define rho sub sigma to be a rescaling so that rho sigma hat is just rho hat of sigma t. So as sigma gets small, the support of rho hat gets larger. So at the end of the day, we will end up taking a limit as sigma goes to 0. And now I will smooth this spectral cluster operator by convolving with rho sigma in the lambda variable, which on one side it is convolution. And then if I use the Fourier inversion formula, I can write that as a product. So on the Fourier side, I have rho sigma hat, and then this 2 sine of epsilon t over t, which is the Fourier transform of this characteristic function. And then it's the Fourier transform evaluated at lambda minus lambda j. And now I will conveniently rewrite this in terms of the half wave kernel. I will collect up the sum over j, the e to the it minus lambda j, and then this sum of the eigenfunctions, vj at x, vj at y, to write this as the inverse Fourier transform of these cutoff functions times u sub t, where u sub t denotes the Schwartz kernel of the half wave operator, e to the minus it square root plus. So a little bit of Fourier transform trickery in order to rewrite the smoothed out spectral cluster as an inverse Fourier transform of the half wave kernel. Now, for convenience, I'm going to collect up all those cutoff functions and the Fourier transforms of cutoff functions and lump them all into one object that I'm going to call psi hat. And it depends on 2 parameters, epsilon and sigma. So I have that the smooth spectral cluster is the inverse Fourier transform of this psi hat times the half wave group. And then it is well known that that u sub t is an FIO of order -1/4 with a well-defined canonical relation that has the following properties. In particular, that the canonical relation is defined as the set where xc in the cotangent bundle is related to y eta via this et, which is the geodesic flow. And there's another relation on the dual variable to t plus norm c being 0. But the important thing is this piece here, that xc needs to be related to y eta via the geodesic flow on the cotangent bundle, which tells us that the singularities of the half wave kernel live exactly at the place at the times t that correspond to the distance between x and y, because you need enough time to get from x to y when you move via the flow. And the fact that the flow is periodic on a Zoll manifold allows us to say that not just are the small time singularities at plus or minus the distance, we also know the singularities for all time, because they will occur again when we travel by a multiple of the period capital T. And then again, and then again, and then again, because we keep looping around due to the symmetry of the Zoll manifold. So we have a characterization of where all of the singularities of the half wave kernel lie. And the singularities are what we care about, because when we take the Fourier transform, that will turn into growth in lambda. Because something that's smooth, you take its Fourier transform, it's rapidly decreasing. If you take something that's singular, take its Fourier transform, it will have some amount of growth to it. So what we care about are where the singularities of this u sub t lie, and then we'll compute what happens when we take the inverse Fourier transform. So as long as the distance between x and y is small, we can localize near each multiple of this period, capital T, and have essentially all of the important stuff from the half wave kernel. All the rest will be smooth, and so its Fourier transform is rapidly decreasing. So we can write this smooth spectral cluster for the distance between x and y less than some delta as the following. I'm going to have a sum over all multiples of the periods. That's a sum over k in z. I will have some oscillatory factors that come from the fact that I'm taking an inverse Fourier transform. I'll have the inverse Fourier transform of the wave kernel at t plus multiples of the period times this thing that I'm calling fk hat modulo some error that is rapidly decreasing. And the rapidly decreasing error comes from the fact that everything away from the multiples of the period is smooth. So its Fourier transform is rapidly decreasing. Now this fk hat is, once again, a bunch of cutoff functions kind of all combined into one object just for the sake of notation. The important fact is that it localizes near multiples of the period in small intervals that depend on these parameters, sigma and delta. Now, we are going to continue using some Fourier transform trickery in order to write this in an even more convenient fashion. You can use the fact that the half wave group acting on eigenfunctions is very explicit. We just get a multiplicative factor, e to the minus it lambda j, times the eigenfunction again. This is just the functional calculus for the Laplacian. So that combined with properties of the Fourier transform allows us to write this inverse Fourier transform of fk hat times the wave group as a convolution, because multiplication on one side turns into convolution on the other, of fk convolved with the spectral projection onto the interval 0 to lambda. So it rears its head even in this case, even though we started with a spectral cluster, we still get the full spectral function showing up. But it is precomposed with u evaluated exactly at k times t. And then there's this derivative in lambda that appears because we're working with the spectral measure appears in the course of this calculation. So I've skipped some details, but the important thing to note here is that I've been able to rewrite something that was in terms of u at t plus k times capital T, in terms of just u at exactly multiples of the period. And the reason why this is so useful is that on the left-hand side, it has some FIO, but u at exactly multiples of the period can be expressed as a pseudo-differential operator, which is much easier to work with. And in fact, it's a pseudo-differential operator with a very nice periodicity property. So this is proved by Duistermaat and Gilliman. If we let this mathrak be pi times a over 2t, remember a was that common Maslov index of all of the periodic geodesics, then u at every multiple of the period can be expressed as essentially the identity plus a lower order pseudo-differential operator of order -1 times this exponential factor that depends on both the period and that common Maslov index. But essentially, going around one full period doesn't do a whole lot to the half wave group. We pick up this exponential factor and we get a lower order error, but more or less, we get back to where we started with the identity, because u at times 0 is the identity. So this is the main reason for going through all the trouble of rewriting things in this way, because understanding the wave group at multiples of the period is very straightforward. So we now have, after all that, a somewhat ugly looking expression where on the left side I have my smoothed out spectral cluster, and on the right I have this sum over all multiples of the period of these quantities that I had written on the previous page, and this d lambda of fk, sorry, this should not be a hat, involved with the spectral function precomposed with the identity plus something lower order. And then we have this piece out here, this exponential factor, which looks like e to the I k t times lambda minus that b, which was defined in terms of the Maslov index. And this exponential factor is actually the reason why we choose those nu sub L, the centers of our clusters, to be defined in such a particular way. Because if we choose lambda to be these nu sub L, which I will remind you are defined in this way, this oscillatory factor is just identically 1. We get e to the 2 pi times something. And so these oscillatory factors all cancel out, which makes the calculation significantly easier to handle. So this is why those oscillatory factors are so, or rather that choice of nu L is so important, is to get rid of this oscillatory factor in sum. So now our next goal is to figure out what are the asymptotics of these weird looking convolutions, where we take fk convolved with pi 0 lambda, precomposed with the identity plus a lower order perturbation. So that's the content of the next proposition. So this does not depend on the Zoll property. The Zoll property shows up in those exponential factors, but for just this piece, this is valid on any manifold. So we let Q be some order -1 pseudo-differential operator with polyhomogeneous symbol. So Q minus 1 will be its principal symbol. And we choose some smooth function f so that its Fourier transform is smooth and compactly supported. Then we can find constants C1 and C2 so that if my distance between x and y is small, we have that these objects that I'm interested in, these weird convolutions, look like the following. They look like, to leading order, lambda to the n minus 1 times an integral over the unit sphere in the cotangent bundle. We have an oscillatory factor that is exactly what shows up in the Weyl law expansion. And the amplitude is like 1, comes from the principal symbol of the identity, and this 1 over lambda times q negative 1, which comes from the principal symbol of q. And all of the leftover stuff is grouped into this remainder r, where we have a fairly precise bound on r. We take the supremum over x and y, which are at most delta apart. And we have a bound that has 2 main terms to it. One is like lambda to the n minus 1, one like lambda to the n minus 2. And the lambda to the n minus 1 looks concerning initially because it is sort of competing with what I'm claiming is the leading order term in the expansion. But there is some stuff that saves us in this very explicit coefficient. So C1 is some constant that does not depend on any relevant parameters. And then we have a factor of delta. So this is why taking the distance tending to 0 is important, because if I were not sending delta to 0 at the end of the day, I would get something that is competing with my leading order term. So this factor of delta here is what saves us when we ultimately take the limit as we approach the diagonal. But because all we're looking for is a little o rate of convergence, we don't need to impose any particular rate for delta to tend to 0. And the proof utilizes sort of short-time Hormander parametrics for the half-wave group. It's fairly standard for the most part, although we do have to be a little more careful about the coefficients in the remainder term, because we need to know how these things depend on the lower order term q and on the smooth function f. So I'm not going to go through the proof of this because it is somewhat tedious and fairly standard. We're just going to go ahead and use this in order to compute the asymptotics for the smoothed out spectral cluster. So as I've said before, if we set lambda to be these special sequence of new L's, we can combine the previous proposition along with some Poisson summation formula trickery in order to write down the next proposition, which is the asymptotic properties of the smoothed out spectral cluster. So I will define the remainder quantity R epsilon sigma to be the difference between the smooth spectral cluster and the thing I'm claiming is the leading term. And we can show that if we take the appropriate limits in the correct order, we do indeed get 0. So we get that the remainder is like little o of nu sub L to the n minus 1, where we take first the supremum over all x and y in this neighborhood of the diagonal. We take the lim sup as we go out in the spectrum, and then we'll take this free parameter sigma to 0, and then finally we take the distance to 0 at the end of the day. So it is a bit of a mouthful to go through all of these limits and lim sups, but it does turn out to work. So we know that the smooth spectral projector, excuse me, the smooth spectral cluster has the right asymptotic behavior as L tends to infinity. Now we need to show that introducing this smoothing, this rho sub sigma, didn't actually mess anything up. We need to know that taking the convolution with rho sigma actually does not affect the asymptotic behavior in a meaningful way. So that's going to be the next objective, which is to control the difference between the original spectral cluster and the smoothed out version. So in order to compare these, I will note that I can rewrite this difference as a sum over J, this spectral sum where the coefficients are what I have defined as H epsilon sigma, evaluated at the difference between nu L and lambda J, where this H epsilon sigma is essentially exactly what it has to be. It's the difference between the sharp cutoff onto the interval minus epsilon epsilon and its smoothed out Fourier transform. Recall that this sine of epsilon t over t is what you get when you take the Fourier transform of this rough cutoff. We've just introduced this extra rho hat of t that makes the support on the Fourier side compactly supported, and therefore, as a function of lambda, it's smooth. Now, it's fairly easy to show. Well, I mean, you can use Cauchy-Schwartz to show that this right-hand side is bounded by two quantities that are evaluated on the diagonal raised to the power 1/2. So I haven't really done anything here other than use Cauchy-Schwartz. And we can also obtain a fairly easy bound on this function H epsilon sigma. It's fairly easy to show that this thing is sort of rapidly decreasing away from where lambda equals epsilon. So this h function is strongly localized near the edges of my interval, which should somehow make sense because h is defined as the difference between this sharp cutoff and the smooth cutoff. So I'm essentially comparing a sharp cutoff like this to a smoothed out version that looks more or less like that. And so the difference between these is strongly localized to the edges of that interval, which is where lambda is roughly like epsilon. And there's this extra dependence on the parameter sigma that shows up. But broadly speaking, it is rapidly decreasing away from the boundaries of the interval. And this is going to be a very helpful property as we go forward. And in order to obtain the correct bounds on this difference, we only need on-diagonal upper bounds for the spectral clusters, because I've used Cauchy-Schwartz to write this in terms of two quantities, one evaluated just at x, the other evaluated just at y. And it will turn out that that is good enough for this piece of the argument, because we just need an upper bound. So for each L, I'm going to decompose that sum over J into three distinct regions. And of course, there's another typo in here. But so first, J1 of L, excuse me, is this region where the difference between lambda J and nu L is bounded below by pi over T. So we're sort of far away from the nu L in region 1. In region 2, the difference is small. It's like some parameter r, which for now is just some positive number, times L to the minus a half. So this is a shrinking neighborhood of the nu sub L as we move farther out in the spectrum. And then this third region is the intermediate region, and it's not LaTeX 8, the middle here, but this should again be the difference between lambda J and nu sub L. So this is the intermediate region where the difference is between this RL to the minus a half and this pi over T. And the reason why we use pi over T is because it is half the distance from one nu sub L to the next. So we're just making sure we are well away from the next nu sub L when we do this. And in both J1 and J2, we can use the rapid decay properties of this H function combined with just very general Weyl law properties to obtain good enough upper bounds so that as we take all these appropriate limits, we could show that the difference between the smooth and rough thing is sufficiently small. It's really in the intermediate region where there is some work to be done. So in the intermediate region, the properties of the H function no longer help us because we're in that region where we're in the interval or near the boundaries of that minus epsilon to epsilon interval. So we don't get to abuse the rapid decay of H. However, we can utilize the fact that the Zoll eigenvalues are very strongly clustered near the nu L. So intuitively, there shouldn't be all that much stuff in this region J3 because we are outside of this L to the minus a half interval around nu sub L. So we should be able to show that there isn't that much stuff in this region, which will help balance out the fact that H is not rapidly decreasing here. So for this, we need to prove yet another proposition, but this one only needs to hold on the diagonal. And the essence of the statement is that the mass of the spectral function is concentrated in these little L to the minus 1/2 intervals around the sequence nu sub L. So on any Zoll manifold with a uniform period T as before, then we can fix any R positive and find constants K, C, and lambda naught, so that for any X in M and any lambda sufficiently large, the sum over all lambda J in this set A, which I will define in a moment, of the on-diagonal eigenfunctions is bounded below by this factor 1 minus C times R to the minus 2 times the sum over all eigenfunctions in this potentially large window, lambda J minus lambda less than capital K. So what is this capital A that I've defined here? Well, it's everything in the window of width K intersected with all of these little lambda sub, or excuse me, nu sub L intervals. So we have these little lambda to the minus 1/2 with intervals centered around each of the nu L, intersected with everything in the giant window of size capital K. So what this essentially says is that if you're looking in some large window of eigenvalues, most of those eigenvalues are contained in this union of little shrinking windows centered on the noose of L. And this is demonstrated as we take the limit as this R gets closer and closer to 0, this quantity will go to 1. And so you're essentially getting all of the mass of those eigenfunctions concentrated in these little windows. And the sort of complementary fact is that everything outside of these shrinking windows is largely negligible in the limit as R goes to 0. So this is the thing that helps us deal with that region J sub 3, where we don't have the rapid decay of that coefficient function H. We get to show that there's really just not all that many eigenvalues in here. And so the sum is, once again, sufficiently small. So as I said, most of the mass of the spectral projector is concentrated in these tiny little windows around the noose of L. And the paper of Buistamaat and Gilliman proves a similar result, but only for the trace. So they prove an integrated version of this, where you show that the counting function corresponding to each of these intervals satisfies this kind of density property, where most of the eigenvalues are close to the noose of L, and there's more or less negligible stuff outside of that. And as I said, this proposition allows us to control that sum over J3 in this limit as R tends to 0. So all that to say that if we combine all of the pieces that we've presented so far, you have that the difference between the rough projector and the smooth projector is sufficiently small in the limit as sigma goes to 0. So I'm taking the lim sup as we go farther and farther out in the spectrum, and then we're taking this parameter sigma to 0, which I'm allowed to do because the original spectral projector did not have a sigma in that. I introduced sigma as a free parameter to play with, and we can prove that this difference indeed tends to 0 as sigma tends to 0, as long as we scale by the appropriate power of nu sub L. So this allows us to conclude that introducing this smoothing factor does not change the asymptotics of the spectral projector. And that is the completion of the proof modulo quite a few details that I've left out for the sake of everyone's sanity. But with that, thank you for your attention. And here are some references in case you are interested in reading some more.
Thanks a lot, Blake, for this talk. We have some time for questions now.
Yes, I have a remark. It's Yves Colin-Verdier. I have a remark concerning your proposition 3. Okay. It seems, as far as I remember, in my paper of 79, I prove that if R is large enough, there is all eigenvalues are there. It means that in some sense, your operator, your Laplacian, is the sum of an operator whose eigenvalue are only the new L and a bounded operator. So if you take the square root, you get that. So it means that if you keep the Laplacian, all eigenvalue for L large enough are in some interval of fixed size around nu L or nu L squared. Then it means that if R is large enough, you have no more. In this proposition, you have 0 eigenvalue if R is large enough. Means that you have you can remove the C if R is. But I'm not sure because it's a quite ancient paper. But as far as I remember, I prove that. So your main object is that your Laplace is the sum of two operators. One is has the same spectrum as the sphere, so with big multiplicity, and the other is a bounded pseudo-differential operator, which commutes with the other. So I guess that it's even stronger than your proposition 3.
Very interesting.
Okay.
I will take a look.
I'm not entirely sure, but more or less. Because those clusters are really clusters. There is nothing outside the interval of fixed size. And
yes, I'll definitely take.
I prove that there is a limit distribution on the eigenvalue in the cluster because it's you have two operators which are commuting. In some sense, it's there is an integral of the,
okay,
and there is a limit distribution, which can be, okay, what it is. So it can be extended to, for example, Schrödinger. You take Laplace on the sphere plus the potential, and I guess it's exactly the same picture, but in this case, V is bounded. Okay, so it's okay.
okay.
And there is a previous paper by Alan Weinstein where he showed already the limit distribution, but I guess he was not proving that the interval the cluster are really bounded for, not for the square root. For square root, they are streaking, as you said, in 1 over r square or something like that. Okay. No, thank you. You have to check my paper. It's in French. I am sorry, but
It's okay. Thank you for that. Yeah, we certainly do not claim that this is like the sharpest possible result you can get.
No, but it will maybe simplify a bit the proof. I don't know, but
yeah, I'll definitely take a look at that. Thank you.
Okay, thank you.
Thanks a lot, Eve, for the remark. Do we have other questions for Blake?
It's about my first question during the talk. If you assume that you have these two commuting operators, so it's Laplace zero, which is this big multiplicity, plus a bounded pseudo-differential operator, okay? Then you can assume, which is more or less generic, for example, if you take delta plus V, then that you have a limit distribution, which is an absolutely continuous measure on these clusters. And then maybe you can center your interval inside this the support of this measure, small enough so that I don't know. I'm not sure, but it seems there is no. If the limit measure is absolutely continuous, the center plays no much role. Every point inside the support should behave the same way. I'm not sure. We have to check that. But
that makes sense.
For Laplace plus potential, the limit measure is simply you take the Radon transform of the potential and you take the image of the Weyl measure by the Radon transform. Radon transform is simply you take the average on closed geodesics. Give you some new function of the cotangent space, which is smaller because you average, okay? And you take the image of your Weyl measure, or normalized Weyl measure on the unique bundle by this function, okay? By this Radon transform, and you get the image measure. And for a generic potential, it's an absolutely continuous measure because there is no places where the places where the Radon transform is constant are all of measure zero in general, not always. But, okay, so you have no Dirac meshes in the. But if
right, so you shouldn't run into the regularity issues if you put your endpoint at one of the center at one of the okay, that makes sense.
You have discontinuities at the boundary in general, not always for the potential because it's like it's not constant. It's like a quadratic form or something like that. So the density is still continuous at the boundary of the interval. And then, but the derivative is not continuous in general. It's like just there is some angle. Depends on the dimension. You have to, but you can exchange further if you want to by email. It's not a problem.
Yeah, I'll take a look at that, and I'll let you know if I have more questions because it sounds very interesting. That it would be nice to kind of not have to worry about exactly where you center the clusters.
Yeah.
Thank you.
But thank you for your lecture. It's a bit technical to expose.
Yeah, some of these are
to present this because it depends of if people know already something about wave equation, the Sturm-Giemann, and things like that. And
yeah, in this in particular,
people remember that it's quite whole story.
Yeah, either you know the kind of baseline or you don't, in which case you're either maybe a little bit bored or just completely lost.
Okay. So bye. Thank you very much again.
Thank you.
Thanks a lot again. Do we have other questions for Blake? Don't. So thanks a lot again, Blake, for this very nice talk and for this intuition about propagation of waves on the Zoll manifolds. Next week, we will reconvene with the gemstone mini course, so it will not be only on Monday, but also on Wednesday and Friday. Back to normal time for everybody because the time changes align back. And it will be Laura Monk who will talk to us, give us a mini course about the geometry and spectrum of random hyperbolic surfaces. So again,